In the previous video, we talked very briefly about strong acids and bases. Strength here is really a measure of how much the forward reaction is favored for those generalized acid and base equilibria. In a way, then, we can effectively think of strong acids and strong bases as complete forward reactions. In terms of the equilibrium constants, Ka will be very large for strong acids, and Kb will be very large for strong bases. As an example, let's look at hydrochloric acid, which is a common strong acid. 1 molar HCl is sort of a misnomer. In truth, if I have a bottle of 1 molar HCl, all of the HCl molecules have broken apart into H plus or H3O plus and Cl minus. So I actually have a bottle of 1 molar H3O plus and 1 molar Cl minus. Strong acids and strong bases completely dissociate. Though there may be trace amounts of the acid or base left over, stay tuned for more on that. But so, common strong acids and bases that you should commit to memory are listed in the book in chapters 15.2 and 15.3. You can assume that everything outside of these lists are weak acids or weak bases. I'm a chemist and a physical chemist at that, so I try to understand and rationalize the world through a few laws of physics, and I leave the rote memorization to biologists. I really don't like having to memorize stuff just for the sake of memorizing it, but to get down to the heart of why these acids and bases make the cutoff for strength goes beyond the scope of this course. That doesn't mean, though, that we can't rationalize more generally what factors contribute to strength and compare strengths against each other. First, we should think about what strong means in terms of Bronsted acids. Recall that Bronsted acids are proton donors, so a strong acid should very easily let go of its proton. In essence, it should have a weak bond to the proton. Take, for example, oxoacids, where one hydrogen atom is bonded to an oxygen atom. So here's my hydrogen, and here's my oxygen. And then that oxygen is connected to another atom or group, typically a halide like fluorine, chlorine, iodine, etc. In this model I have here, I have HClO4, right? So each of these oxygens, the little red balls, and then my hydrogen is the white one, and then chlorine is this central black sphere. And so HClO4 is a strong acid. In the case of oxoacids, if we want to increase the strength of the acid, we need to decrease the strength of that OH bond. Remember that a single covalent bond is really just 2 electrons being shared between 2 atoms. In a strong bond, the electrons are evenly distributed between the 2 atoms. But in a weak bond, the electrons are being pulled away from one atom. So for this acid, that's pretty easy because this whole ClO3 group on the opposite side of the hydrogen is very electronegative, as in it wants the electrons very badly, and therefore it will pull electron density away from that OH bond, allowing the proton to leave. However, as I remove these extra oxygens away from the central chlorine atom, I'm reducing the overall electronegativity of that group. And so hydrogen has an easier time hanging on to that oxygen. This can be summarized as such. In oxoacids, electronegativity is the driving factor for strength, as in a more electronegative atom or group will increase the strength of the acid. Next, we'll take a look at binary acids, which is when one single atom, say in this case chlorine, is bonded to one or many hydrogens. So like this example here where I have HCl or H2S, right? I have one central atom and 2 hydrogens on the H2S. Now, unfortunately, my models are not to scale, so you'll have to use your imagination on this one to determine the strength. But here, the same principle applies, right? A stronger acid will have a weaker bond to the hydrogen. When we're comparing across the same row of the periodic table, say with sulfur versus chlorine, the electronegativity rule is still true. The more electronegative atoms will result in stronger acids. Say, chlorine is more electronegative than sulfur, which is why HCl is a strong acid and H2S is not. But this is only second to the most important factor affecting binary acids' strength, and that's size. Think of HF, or hydrofluoric acid, which is a weak acid. Hydrogen and fluorine are both near the top of the periodic table, so they're generally pretty small compared to those heavier atoms below. So the way I think about them is that hydrogen is holding on to fluorine like my hand holds on to an orange. Even though I don't have very large hands, this is a pretty simple task for me. As the object I'm holding gets larger though, I start to struggle. Pretend this spaghetti squash is a chlorine atom, like an HCl, or that this container of vegan protein powder is bromine for HBr. My hands are just too small to be able to hold on to the other atoms, and that's why hydrogen can so easily leave HCl or HBr. So to summarize, binary acid strength trends. In binary acids, size is the dominating factor, where a larger atom will result in a stronger acid. The secondary factor, which only applies when comparing binary acids in the same row, is electronegativity, and a more electronegative atom will result in a stronger acid. So on top of memorizing that list of strong acids, you can now compare relative strengths based on those factors. Now would be a good time to also remember your periodic table trends, especially regarding electronegativity and size.